All right, this is Unit 4A, Lesson 12, Delso-Schaefer Test Review. So here we go. We are going to talk about physical and chemical properties of matter. We'll talk about that first. Physical properties are those that do not change when you make a change in it. You can cut wood and it's still wood. When the finished products are the same as when you started, that's a physical change. Chemical changes are when substances go through a change and then they become something else. When you burn wood, you then produce smoke and soot and ashes, and that's no longer wood. So that's a difference. Dissolving in solutions. A homogeneous solution is something that's the same throughout. It's all together the same. When you mix salt in water, you produce saline, it's the same. Heterogeneous is like a salad. There are different parts. It's a mixture. It's more a mixture, not a solution. When you are working with solutions, you have a solute and you have a solvent. The solute is that's the solid part that's mixed in. When you make saline, you use salt, that's the solute, and the solvent is the water. How matter changes its states. It changes its states by gaining energy or losing energy. The more energy it has, the hotter it gets, farther apart the molecules and the atoms are. Characteristics of solids, liquids, and gases and plasma. Solids are rigid. They tend to stay in one spot. They don't move very much. As you gain more energy, liquids get them farther apart. They will then take the shape of their container. And then when you keep adding energy, you can get to a gaseous state, and then the particles are very far apart. Plasma is a charged gas. It's different than gas, but it's charged. It will respond to a magnetic field. The sun is plasma. Most everything in the universe that we know of is plasma. Concentrations in solutions up here are calculated by how much solute is in a solvent. So the solute is used to determine a concentration. Electrons and their amount of energy. As electrons get farther from the nucleus, they gain more energy. When they gain enough energy, they can actually escape from the atom, and they can migrate towards another one, or the electron can move away. How properties of elements are determined. Okay, this is our good old periodic table. Hopefully you can see all of it. I think you can. And in our periodic table, it has a little number in the lower left corner on this one, which is a 1, and then it's got this decimal. Hydrogen's at the top, and then the symbol is H. That number down there is the atomic number. That is always how many protons are in that element or that atom. That is what gives them their properties. So the number of protons, which is always equal to the atomic number, gives an element its properties, like a metal or a metalloid or a noble gas. Where are we at? That's how properties are determined. The relative size of the nucleus. If you watch the Disney movie, Rutherford decided when he was shooting the neutrons through the gold foil that the nucleus is extremely small. Atoms are mostly empty space. So relative to the atom, the nucleus is extremely small. What else we got here? Orientation of periods and groups and families on the periodic table. Back to our old friend, and you will need one of these for your test. You'll need this, and you will need a calculator. A period goes horizontally across this way. The first period, which is numbered right here 1, there are 2 different elements. The reason is there are only space in that first period or energy level that will hold 2 electrons. That's why there are only 2. You move down to the second period on the table, and there are 8. 1, 2, 3, 4, 5, 6, 7, 8. We work with this row a lot. Row 3 is the same. It also has 8, and we use sodium a lot, magnesium, aluminum, sulfur, chlorine, all those are used. A family is one that is vertical. This is family number 1, or group. They'll also call it group. The group in 1 will tend to have 1 electron that they will share. So all these have normally a positive 1 charge. This column 2, which is a group, these tend to have 2 electrons that they will share. When you go to the opposite side, when we start going backwards, this one you went 1, 2, this one goes backwards. So these have bonding sites on them. Group 17 tends to have 1. They need 1 more electron to fill their outer shell, and atoms work to do that. So it will take 1. Oxygen tends to take 2. Nitrogen in this row is 3, and carbon's 4. Carbon is very special. That's kind of what the Earth as we know it is built on, is carbon. Every living thing has it in there because it has 4 bonding sites, and it can do lots of tricks and bond in many different ways. 18, group 18, these are the noble gases. They tend to be found just like they are in nature. The reason is because their outer shell is filled, and they are inert. They also are called inert gases, or they used to be when I was a kid. What do we got? We talked about the atomic number. Types of atomic bonds. There are 4 that we are going to talk about today. Ionic, that's the strongest kind, and that's where the electron is almost given to the other. In fact, they used to say it was given to the other. But it is shared so closely with the other one will not give it back up to the original atom. Covalent co means equal, or if you are cohabitating or you're a co-sponsor, both of you sponsor, hopefully equally. So that's a covalent bond. Hydrogen bonds are ones that are formed through hydrogen. They are easy to break. These are kind of weak. Water, you can run a very light electric current through it and it will break. The strengths of the various atomic bonds. Ionic is the strongest, then covalent, then hydrogen. Atoms found in nature tend to have their outer shells filled, or their outer electron energy levels filled. And that's the way you find them in nature. They also tend to have the same number of protons and electrons. Ranking atomic bond strength, we did that. Ionic, covalent, and hydrogen. How atoms form molecules and compounds. They do this by various bonding. They'll use these bonds to come together and they make a molecule. 2 hydrogens and an oxygen will make a water. When we talk about salt, the bonding of salt, it will form a crystal pattern. And it is an ionic bond. It is 1 sodium and 1 chlorine atom that come together. They also will conduct electricity. So that's a very strong molecule, and ionic bonds are strong. Number 17, get my paper over here. Ionic bonds and electricity, we just talked about that. Sharing in covalent bonds is equal. Bonds in the DNA molecule. The DNA molecule has covalent bonds because they can be broken easier than ionic bonds. And if you remember that DNA shape, which is that double helix, for it to replicate, it has to unzip or come apart. To do that, those bonds have to be broken. And if they were very strong, it would take an awful lot of energy to do that. So they are covalent bonds. Bonding sites in the periodic table, we talked about that. Right over here, this one has 1 bonding site, this group. These have 2. Oxygen usually will work with 2. Nitrogen in this group or family is 3. Carbon in this crew is 4. On the other side, these tend to give up an electron, and the ones in this first column tend to bond with the ones over here that have 1 bonding site in 17. You'll see there's sodium and there's chloride. That's what makes the salt. When we get into water, oxygen has 2 sites, so it can take on 2 hydrogens. That's why it will fill that outer shell, and that's where we get water. That's how things work. Why atoms bond to other atoms? They try to fill their outer shell. They're just more stable that way, and that's what they work to do. While water decomposes relatively easily, or easy, those are hydrogen bonds, and hydrogen bonds can be broken, and that's important because water's used, that's one of the foundations of life here on Earth. Bonding capacity of hydrogen. Hydrogen has 1 electron. It has 2 sites, so it can bond to one other. Can only take on one other. It can't take on 2. The noble gases, we talked about those. Those are to the far right of the table. They don't like to hang out with anybody. They're called antisocial. The movement patterns of bonded atoms. Bonded atoms will vibrate. They move. The more energy they get, the farther that vibration or stretching or movement pattern is. You can gain enough energy, it will eventually break that bond. 26. Come on, paper. It's not being nice to me today, guys. What happens is you add energy to a molecule. That's what we just talked about. Characteristics of polyatomic ions. Polyatomic ions are a group of atoms that come together, and they are bonded so tightly or so well, they tend to function as an atom would. They don't come apart very easy. When you see them in chemical equations, keep them together, don't take them apart. Makes things much easier. Charges in the periodic table, we've talked about that a bunch. On the left-hand side tend to be positive, on the right-hand side tend to be negative. The prefix poly means many. A polyester has many esters in it. Bonding sites and the periodic table, we've talked about that. Parts of a chemical equation, I haven't talked about that, and we need to. The parts of a chemical equation are, on the left-hand side, you have reactants. This happens to be how water is formed. We have hydrogen and oxygen atoms. They combine together. This arrow means yields. It's kind of like an equal sign in a math equation. When we use the computer, we have to use the arrow. That doesn't mean greater than. These are equal. It means it yields in this direction these products. So we have reactants on the left, yields products. Products are on the right. Hydrogen and oxygen are combined together with energy, and they form water molecules. Remember, all the atoms on the reactant side have to be on the product side. They have to balance. When you are calculating the mass of a chemical reaction, only use one side. Don't add both of them together. That's a common error. One side is, it's called the law of conservation of matter. It can't be created or destroyed. It can change from matter to energy, but that takes an enormous, enormous force. So everything on the left is equal to everything on the right. What elements to balance last? If you'll remember the lady from the video, and she was very good, use hydrogen and oxygen last in that order. Balance your other stuff in the equation first. Polyatomic ions and balancing equations, leave them together. Look at those as kind of their own thing as an atom, not as the atoms breaking them together. Leave them together. Subscripts and coefficients. All right. A subscript. This is a subscript in H2O. It's written behind one of the atoms in the molecule. It only applies to this one that's in the front. You cannot change subscripts when you're balancing. The numbers in the front are coefficients. Those are the ones you change, and you have to change those to make them balance. Do not change subscripts, change coefficients. Calculating chemical reaction atomic mass. This is probably the hardest skill that we're going to do on this test. How many grams of oxygen does it take to make 1 gram of water, H2O? The first thing you have to do is find out how much a molecule of the water weighs. And in this case, we have molecule of water weighs 18.015 atomic units. It has 2 hydrogens. Each of the hydrogens, when you look on your periodic table, that's the atomic mass number, 1.0079. We round to the third, it's 1.008. So we have 2 of those. And then we have an oxygen over here, and it's 15.999. We have 1 of those. There's the 1008, it's times 2, and then we have 1 oxygen, 15.999. We add those together and get 18.015. Now, to get 1 gram of it, we have to divide that total number, which is on the whole molecule, and then we divide how much we're looking for oxygen. The oxygen's 15.999. We got that from the chart. We divide that by the 18, and we get 0.881 grams of oxygen. A hint, if you are looking for 1 gram, if the answer you get is above 1 gram, you've made an error somewhere. You're using the wrong numbers. It has to be less than what the total would be, in this case 1 gram. So that's how much oxygen it takes to make a gram of water. Chemical reactions and the law of conservation of mass and energy, it follows it. You can't create or destroy. That's why you have to balance equations. They have to be balanced. The left side has to equal the right side. Don't add them together when you're calculating the mass involved in an equation or a reaction. Balancing equations and calculating atomic mass, that's what we do here. If we are doing the mass of hydrogen peroxide, that's what this is. H2O2 is hydrogen peroxide. Same stuff you buy down at Walgreens in the brown jug. And 2 of those molecules will decompose. This is a decomposition. We're taking it's becoming 2 things. One thing is becoming 2 or more. It yields 2 hydrogen peroxide yields 2 water molecules and 2 oxygen molecules. Okay? To calculate the atomic mass, I have 4 hydrogens. The 2 coefficient in the front and the 2 subscript apply to the H, so 2 times the 2 is 4. 1.008 is the mass, times 4 gives us that number. Oxygen, same thing, this 2 here and this 2 here, equal to 4. When we go to the other side, what's happened is 2 of them bond with the hydrogen, so there's 2 of the 4 oxygens, and then the other 2 are freed up and they go into the atmosphere. We multiply that by 4, we get this number. We add those 2 together, and that is how much 2 molecules of hydrogen peroxide weigh. You'll be asked that. Remember, same on the reactants and product side. This number applies here, applies there. We're getting close, crew. Balancing chemical equations and calculating mass, that's what we did. Calculating masses in chemical equations, same trick, that's what we did. Remember, when you are balancing equations, you can change coefficients. You may not change subscripts. Types of chemical reactions. We have a synthesis. A synthesis is when 2 things combined, hydrogen and oxygen, combine to form water. These 2 things come together. Decomposition is what we just talked about with hydrogen peroxide. We have these 2 things together. Then through the equation, they separate into different things. A single replacement. You have one thing here, and it goes into a compound or a molecule, and it will change places. A has changed place with B. That's all that's happened. Single replacement. Double replacement, two compounds, two molecules or substances are reacted together and they change places. The A and the B trade out. So A will now go, in this case, with D, and B will now go with C. So it's just, they're just replacing, they're trading places. It's the chemical square dance. Combustion, two things. We add enough energy to it and enough heat, it will turn into carbon dioxide and water. That when you see these two products, you are in a combustion reaction. That's the basis of cars, gasoline, natural gases, how we heat our houses. Can be dangerous because this takes up the oxygen, and that's why we have smoke detectors and carbon monoxide sensors in our house. I think that's about it, crew. It is about it. Now, here's the deal. Monday, please watch this thing again. Make sure you can do it. You may have to watch it a few times because I'm going fairly quick. I will be available Monday on the hour, 8, 9, 10, 11, 12, and 1. That's enough. We'll do the same thing on our Tuesday, Thursday meetings. We'll just go on the hour through 1 o'clock. And that's how we'll do it, because some of you have conflicts when I'm only doing it at 10 o'clock. So we'll just do it each hour. And those aren't mandatory. It is mandatory that you get on and do your assignments. If not, we're going to call your parents and we're going to talk about you. So that's never a good thing when we're calling for that reason. So don't go there. All right, guys, that's it. I'll get this up. Hopefully this time it'll do better. We couldn't see the other one, and I'm out.